Thermal radiation is the electromagnetic waves that you see and that you feel off of a hot object. You can tell the lava is super hot because it glows orange and red. Here's a baby picture of our universe. It's the afterglow from the Big Bang. And by looking at the wavelength of the radiation, we can tell that the temperature of this afterglow is about 2.7 Kelvin. Not absolute zero. Space is not absolute zero. There's a remnant heat left over from the Big Bang. Now, the color of like lava or red hot things, the color that they have depends on their temperature. So you know that like when a burner on a stove starts getting really hot, it starts to glow red, and then you know it's around 1,000 Kelvin. The hotter and hotter it gets, it moves through a spectrum of colors. Blue hot is extremely hot, like 10,000 Kelvin, then things glow blue. Stars, for example, illustrate this. There are stars that are red, there are stars that appear white, like our sun, and then there are even blue hot stars, which are extremely hot. So what's going on here? Well, let's look at the simulation. The thing to keep in mind is when something's glowing red hot, that doesn't mean it's only giving off red. It's actually giving off a spectrum of colors. It's just that mainly it's red, or we perceive the color as red. For instance, here's the sun. Temperature of the sun around 5 to 6,000 Kelvin. What this graph is showing us is how much power the sun is giving off, how radiant it is, as a function of wavelength. Along the bottom, it ranges from 0 microns up to 3 microns on this graph of wavelength. So the spectrum that's given off by the sun, it peaks near the green part of the spectrum. Why doesn't the sun appear green then? Well, it's because it's also emitting a lot of red and blue, and our eyes, when they see all those colors together, we perceive it as white light. So that's the sun. Notice, of course, the sun also gives off a lot of UV rays. There's a significant amount of radiation that comes off in the ultraviolet range too. Those cause sunburns. And there's a whole bunch of radiation that's even longer wavelength. That's the infrared that comes off the sun. That's what makes you feel warm. This is just the part we see. This is the part that causes sunburns. And this is the range which we feel as radiant heat out of the sun. But it's all just electromagnetic waves, just different wavelengths. That's the sun. If I dial down the temperature, now it's something like a light bulb. A light bulb appears, let's say, like orange, and that's because it gives off a lot of its radiation in the red and yellow part of the spectrum. Of course, a light bulb also gives off a whole bunch of heat in the infrared part of the spectrum, the long wavelength part of the spectrum as well. What about the Earth? Does the Earth radiate heat? Sure it does. I don't see it on the graph, but that's just because of the scale. Now I can see the Earth's spectrum. I just had to zoom in a lot. I had to zoom out on the wavelength because the radiation given off by the Earth is in the 10 micron range. It's not visible light. Here's the visible spectrum way over there. There's the visible spectrum. The wavelengths given off by the Earth are in the infrared. Warm things like our bodies and the surface of the Earth, they radiate radiation too. It's just you don't see that. It's in the heat part of the spectrum, what we call heat. It's in the infrared part of the spectrum. Now, there are stars which are blue hot. And if I go to the star Sirius A, it's just off the charts. It peaks in the ultraviolet. So huge amount of ultraviolet, you would see it as a blue star. That's in the 10,000 Kelvin range. Okay, so we see how as you dial the temperature down, the peak of the graph moves to longer wavelengths. Here now is the sun. Sun peaks around green, light bulb peaks around, in the red range, and so on. Okay, so that explains this observation, that as things get hotter and hotter, they move towards the blue, because that's where the peak of their that's where the peak of their radiation is. Okay, the feature that we want to focus on now is how the graph gets so much taller as you go to higher temperatures. So for example, the sun is around 5,000 Kelvin. I'm going to put it at 5,000 Kelvin. Yeah, right about there. Okay. The total amount of radiation that comes off is much, much smaller than if its temperature were 10,000. Here's the 10,000 Kelvin object, like this Sirius A star. In fact, it turns out that if you double the temperature, going from the sun to a 10,000 Kelvin object, the energy it gives off doesn't double. In fact, if you double the temperature, it's observed that the energy given off from it is multiplied not by 2, but by a factor of 16. Why 16? That's 2 to the 4th. So in fact, the temperature determines not only the color, where the peak of the spectrum is, but the temperature tells you how much energy flows out of the object by radiation. You're accounting for all the different wavelengths, not just the peak one, but if you account for all the different wavelengths and you ask how much energy flows out of an object at temperature T by radiation, the answer is you have to take T to the 4th power. It's T to the 4th that determines how much energy flows out of a warm object. So let's put that down. The energy flux, meaning the amount of energy that flows out of an object at a certain temperature, I'm going to call it J. I'll say specifically what it means, like what its units are in a second. It's given by a constant, a universal constant, sigma times the temperature of the object to the 4th power. So if you double the temperature of something, it doesn't give off twice the energy flowing out of it. It's 16 times the energy that flows out of it. This accounts for all the different wavelengths, UV, visible, and infrared. Okay, so this is the energy flux. What do I mean by energy flux? It's the energy flowing out. It's the energy flowing out per second per square meter. So it's how bright the object appears. So the units of it are joules per second per meter squared. In other words, watts per meter squared. It's the intensity of radiation coming off of the glowing object when it's at a certain temperature. Okay. The value of sigma is called Stefan's constant, and you can look up its value, what it is. It's a universal thing. Now, this is the optimal brightness of an object that's at a certain temperature. This is in fact what we call the black body energy flux. Other objects, like things that aren't, and that name sounds weird, and I'll explain why it's called a black body, because what I'm saying is when you heat up an object, it's glowing in all these different colors. Why in the world am I calling it a black body? You just have to hold your breath for a minute on that. We'll see. Turns out that black things emit in the most optimal way when you heat them up to a certain temperature. This is the energy flux of a black body. Actual objects, which aren't totally black, which sometimes are called gray bodies, they have an energy flux which is somewhat less than the optimal value. For instance, here's the energy flux out from the Earth. The Earth glows in infrared. If you had infrared glasses, you'd see the Earth glowing. That's how telescopes see these exoplanets, on distant stars. they see the infrared glow coming out of the planets. So here's the optimal, what we call the black body spectrum from the Earth. But the actual spectrum from the Earth, it's suboptimal. It's somewhere below that. There's some losses that occur. So it doesn't glow quite as bright. It does peak in the right place, but it's suboptimal in terms of how much energy flux there is. So that's easy to account for. Actual things which aren't totally black, but are like gray, you just have to multiply by a factor. E is called the emissivity. And its value, if it's optimal, it's equal to 1, meaning it's like 100% of the possible energy flux. But an actual object, maybe it's only 50% of the optimal value. The point is the value of E can range from 0 to 1. It's like a percentage. Something which is 100% optimal in terms of its emission of radiation, E is equal to 1. If it's terrible, it's near 0 and hardly emits anything when it's warmed up. So we call that E value the emissivity, how good it is at emitting radiation. Okay. Let's talk for a second about absorptivity and reflectivity. Something which is very good at emitting radiation also has to be very good at absorbing radiation. In other words, it turns out the value of E is equal to the fraction of radiation that the object absorbs. A picture might help. If something's completely black, what we call a black body, then it absorbs radiation and it emits at the same rate. It's just as good at absorbing as it is as emitting. This is the absorption part, this is the emission part. In other words, if it's optimal at emitting radiation, it's also optimal at absorbing radiation. And that's why we call the things with E equals 1 black bodies. Because if they're very good at emitting radiation, they are going to appear totally black because they're also good at absorbing. Things which are gray, they don't absorb everything that hits it. Some part of them reflects off. And that means they don't emit, quite as good. The point is that the emissivity value is equal to the absorptivity value. Why does this have to be true? Suppose I have a cup of coffee and it cooled off to room temperature. It has to emit at the same rate that it absorbs radiation. Otherwise, it's going to spontaneously get hotter and hotter just sitting in the room, which we know is nonsense, doesn't happen. Any object emits just at the same rate that it absorbs. Otherwise it would never reach equilibrium with the room. It would just keep, if it absorbed better than it emitted, then wouldn't it just get hot? The coffee would spontaneously get hotter and hotter, which is nonsense. So the E value is always the same for the A value. If E is equal to 1 and it's a super emitter, then it's also a super absorber, and hence the name black body for E equals 1. Okay. A is the percent that it absorbs, but isn't the percent that it absorbs just whatever's left over from reflections? In other words, if something reflects 20% of the radiation that hits it, then that means it's absorbing 80% of it. 1 minus 0.2 is 0.8. So if you know the reflectivity value, you know the absorptivity, these are like fractions, and then you also know the emissivity value. So that's typically how problems go. You know the value of R, you know that something reflects 20% that hits it. That means the absorption factor is 0.8 and the absorptivity, the emissivity is also equal to 0.8. Okay, so let's look at some problems. Here we have an infinite sheet of black material. It's at some temperature T. So it looks like this. This thing is at a temperature T. It radiates into its surroundings, which is a vacuum. So it's like in space. And there's a heat shield, which is just a parallel black sheet placed next to it. Questions are things like, what temperature does the heat shield reach? Find how much radiation is emitted into the surroundings with the heat shield in place. Like if this thing's a shield, it must somehow reduce the amount of radiation coming off the high temperature object. What if we put another heat shield in place? How does that affect things? And then what if the heat shield is gray, like it's not perfectly black? And we'll look at all those things. Um, this is an idealization of an astronomy type problem. This could be the star at some temperature, like the surface of the star. And stars are often surrounded by dust. How does the dust shield or cloud of dust around the star affect the heat that comes out of the star? These are all important questions that astronomers have to be able to account for. Okay, so let's draw the heat flowing in and out of all the different parts. Remember, this part is at temperature T. I'm assuming like it holds its temperature. The star is maintaining its temperature. Let's draw the energy flux that's happening everywhere. This thing, it's black, totally black. So it's sending out radiation from its surface, which I'm calling J. It depends on T to the fourth power. Okay. Now the shield's going to absorb that radiation. It's also totally black, so it's going to absorb all of it. No reflections are going to come off its surface. However, it is going to warm up when the radiation hits it, and it's going to radiate out in both directions. And I'll call those J1. Both sides, I assume, are perfectly black, so they're going to emit at the same rate on both sides. Okay, so what do I do with these? Well, the key idea here is the idea of thermal equilibrium. You see, if the heat shield starts off at absolute zero, it's going to start warming up more and more and more. Why is it going to warm up? Because more heat is going to be absorbed by it than it's giving off at first. At first, it's cold and emits very little. But as it gets hotter and hotter, it's going to reach a point where the heat coming into the shield matches the amount that it itself is emitting out from its surface. And when that happens, it's going to stop gaining temperature, and it reaches what we call thermal equilibrium. In other words, heat in matches the heat out from the shield. When that happens, its temperature stops going up, and we reach an equilibrium, a static situation where the temperature is no longer changing. Okay, so how much heat is going into the shield? That's just the value of J. There are no reflections to worry about at this stage, so the heat that comes into the shield is just the same as what's coming out of the surface of the star. How much heat is coming out of its surface? That's 2J, 2J1. It's coming out from both surfaces. It's black. Both things are totally black. Okay. Hopefully you know what I mean when I say that. When I say they're totally black, what I mean is they're black bodies, meaning that they're perfectly absorbing. Of course, it's a surface of a star, so it's just searing hot and giving off tons of light from its surface. It doesn't look black, but it behaves as if it's perfectly absorbing and optimally emitting as well. Okay, so this means I can solve for J1. J1 is equal to 1/2 of J. That lets me figure out the temperature. It's telling me that J1 is equal to 1/2 of the energy flux from the star. And now what I know is These are J1 goes like T1 to the fourth. So this is an equation to solve for the temperature of the shield. It tells me that T1 must be 1 over 2 to the 1/4 power times the temperature of the star. This is T to the fourth. This is T1 to the fourth. I take the fourth root on both sides. So it's interesting, the heat shield doesn't reach the same temperature as the star. The star sends out radiation in one direction out from it. The shield emits radiation in both directions. And for that reason, its temperature is less than, the energies can balance with the shield at a lower temperature than the temperature of the star. We kind of know that because it's not like the Earth's temperature matches the temperature of the sun. It's an energy balance that's reached, not necessarily a temperature balance. Okay, let's look at the intensity of the radiation emitted into the surroundings with the heat shield in place. Well, we already have that. That's just J1. In other words, the amount of heat which comes out into the environment is now 1/2 of J. In other words, the heat shield does serve its purpose. It cuts the radiation in half. So we're done with A and B. What if there's an additional heat shield that's in place? Well, this is shield number 1 and this is shield number 2. Shield number 2 is going to, of course, warm up from the radiation it gets from shield number 1, and it's going to emit its own radiation. Now let's see how this works. Now I can look at shield number 2 and notice that J1 must equal 2J2. So this is part C. I must have that J1 is equal to 2J2, that's shield number 2. In other words, J2 is equal to 1/2 of J1. In other words, by putting another heat shield there, the heat flowing out drops by a factor of 4. This is 1/4 compared to the heat flowing directly out of the star. So multiple layers of heat shields, they each drop the heat flow out by a factor of 1/2. Now, what if the heat shield is partially reflective? What we call like a gray body, partially reflective. Then the star is still emitting its energy flux, but now the shield is going to reflect some fraction of it back. It reflects a fraction R times J. The sheet absorbs the rest. It absorbs the percent 1 minus R, and then it emits at that with the same, in other words, the absorptivity factor is 1 minus R, and so the emissivity factor is also 1 minus R. That means the shield is now going to emit radiation. It emits it at the rate not just J1, but 1 minus R times J1. J1 would be the black body energy flux. Now it's lower than that. The principle is the same. What's coming in to the into the shield must balance whatever's coming out. So we have to have in equals out at equilibrium. What's coming in is J. What's coming out is 2 times 1 minus R times J1. From the emission on both sides of the shield. And also what's coming out is the reflected part plus RJ. So this gives us a solution for J. This, remember, J refers to the black body emission. So this tells me that J1, the R's actually cancel, and I find that J1 is 1/2 J. That's just like before. That implies that just like before, the shield reaches the same temperature as it is when it's black. This implies that T1 is 1/2 to the 1/4 power times the temperature of the star. However, it means that J1 is the T to the 4th emission rate. We're asked to find the intensity of radiation emitted into the surroundings with the heat shield in place. That's 1 minus R J1. So this gives our answer for part A. For part B, we have that it's 1 minus R J1. Remember that 1 minus R, that's the emission rate. The emission, or I shouldn't say rate, the emission factor, the emissivity, is equal to the absorptivity, which is 1 minus the reflection factor. And this is just 1/2 times 1 minus R times the energy flux from the star. So if the object's gray, meaning it's partially reflective, then it's an even better heat shield. Although it reaches the same temperature as if it's a black body, now it's partially reflective, means it's worse at absorbing, and therefore it's somewhat worse at emitting as well. So it's an even better shielding effect the more reflective the shield is. If you've seen like survival blankets, they're foil blankets. They are terrible at absorbing radiation, and for that reason, they're also terrible at emitting radiation, which is great for a blanket. They really hold the heat very well. They're also kind of airtight, which prevents convection. In this example, we have two objects at different temperatures. For instance, it could be, this is very cold, T1. This could be like liquid nitrogen. And then you want to keep it separated by a vacuum from the surroundings, which are at like room temperature, and that's T2. Heat will flow from 2 into 1 and eventually boil off all the liquid nitrogen. First, we want to figure out the energy transfer between these two, between the two things, and then we'll repeat it if there's a reflective heat shield in between. Okay. So first, they do both emit radiation. Even though this one's liquid nitrogen, it's super cold, but it still emits thermal radiation out of it at the rate J1. I assume they're black bodies, so I'm using just the value of J. And this one is hotter, so it has a higher emission rate, J2. The amount that's transferred between the plates, in other words, how much is going from right to left, I just subtract, call it J. The net heat transfer is J2 minus J1. In other words, to be clear, this is sigma T2 to the 4th power minus sigma T1 to the 4th power. That's the net energy flux from one to the other. Okay. Now, with the heat shield present, let's see how it changes. Now there are going to be reflections, off the heat shield. This one still emits in the same way, J1. This one emits J at J2. But now we've got a reflective heat shield here. That means it reflects that fraction of J1 back to it. There's RJ1. And it reflects that fraction of J2, RJ2. It does absorb some of it. And remember that the amount that it emits is equal to the amount that it absorbs. So I'm going to label this thing with a number 3, because it's the third thing. And so It's absorbing at the rate 1 minus r times J3, and it's emitting at that same rate. This is 1 minus r J3, 1 minus r J3. I'm using the fact that this shield in the middle is going to reach some temperature, T3, and it emits accordingly. Its emission rate, which would be E times T3 to the fourth, E is equal to 1 minus R. So that's the rate of emission. Okay, so I'll first figure out the temperature of the shield and then see how it affects the net flow of energy. Okay, so to figure out the temperature of the shield, like before, I set in equals out. Whatever's coming in towards the shield, I set equal to what's coming out of it. So that means what's coming in is J1 plus 2. What's coming out of it is RJ1 and RJ2. That's R J1 plus J2. And also there's two of the emissions from equal ones from both sides. That gives me an extra piece, 2 times 1 minus R J3. This is an equation to find the temperature T3. I simplify. The 1 minus R cancels on both sides. Just like we saw in the previous one, the reflectivity part doesn't actually affect what temperature it reaches. So what I find is this. I find that J3 just comes out to be the average of J1 and 2, 1/2 J1 plus J2. And then I take the fourth root of both sides to figure out T3. T3 will be the fourth root of 1/2 T1 to the fourth plus T2 to the fourth. So it reaches kind of like an average temperature, not really average because it's the average of the fourth powers of the temperature, and then you take the fourth root. But that tells you the temperature. It's really similar to the previous problem, it's just now you have energy coming in from the other side of the sheet as well. That has to be accounted for. Okay, now we want to figure out the energy transfer that occurs with the shield present. Now I want to compare the effect of the shield with the value of J. In other words, J meant the flow from right to left. And I want to compare now that the heat shield is in place. So what I'll do is I'll look at the right half and I'll compare, not compare, but I'll look at how much energy is flowing from right to left on the right side of the sheet. So I'll call that J prime. J prime is going to be J2 coming off the high temperature thing, minus RJ2 minus 1 minus RJ3 from the emission from the heat shield. This gives me 1 minus R times J1 minus J3. I plug in the value of J3 and I find that it's 1 minus R over 2 multiplied by the difference J2 minus J1, which is just equal to J. So that's how I can directly compare the heat flow with the shield there compared to what it was without the heat shield there. For example, suppose it's very reflective. The heat shield is very reflective. That means R is like 95%. Okay. Then 1 minus R is 0.05, and you would find that J prime is 1/2 of 0.05 times J. In other words, you would find that J prime would be very, very small. It would be 0.02 0.25. Only 2.5% of the original energy transfer occurs if you put that very reflective shield in place. So this is how you construct a very nice thermos called a dewar, which will insulate the liquid nitrogen. You put shiny material in the middle, not just a vacuum. With a vacuum, that's something, but there's still a significant energy transfer that occurs from the surroundings. With the heat shield there, it drops that energy transfer down a whole lot. Keeps the liquid nitrogen cold. Called a dewar. D-E-W-A-R. Human body temperature is like 98.6 Fahrenheit. So we're actually radiating electromagnetic waves out from our bodies. The question is, what's that rate? What's the rate of energy loss? How much energy do we lose? Are we like a 100-watt bulb, or are we like a 20-watt bulb, or what? So we're supposed to assume that our skin has an emissivity of about 0.9. That means that the emissivity is equal to the absorptivity, which is about 0.9. In other words, the reflectivity value is about 0.1. We reflect about 10% of the light that hits our body and absorb the rest. Okay, so we're looking at the energy, the net energy loss. Now, you got to remember that, yes, we're emitting heat out with an emissivity factor of 0.9. We also absorb some, because it's not like we're in a vacuum at absolute zero around us. The air around us sends some radiation into our bodies as well. So if I want to know the net heat, J, it would be equal to the sigma times E times the temperature of our body to the fourth. I also have to account for the input as well. That would be minus sigma times the absorptivity of our body times the temperature of our surroundings, call it T naught. We're at temperature T. So there's the emitted, there's the absorbed part. E equals A, so this simplifies to just be sigma, to be just E sigma T to the fourth, our temperature to the fourth, minus the surroundings temperature to the fourth. Now, I also ignored any kind of reflections, like I'm assuming the air doesn't reflect any of the radiation back. Okay, so all I have to do is plug in. This would give me the energy flux from our body. Now, we actually want the power, the net power, which comes out of us. To do that, you have to multiply the flux by the area. You see, this J, that's the energy given off per square meter of our skin. You'd have to multiply it by our surface area to figure out the total number of joules per second. So that would be E sigma times our skin area times T to the fourth minus T naught to the fourth. And that comes out to be about 100 watts. I have 97.8 watts. So our whole body together acts pretty much like a 100-watt bulb in terms of the energy flow. The actual question is, find the net energy loss in 12.3 minutes. So the actual energy, this is energy flux, this is the energy rate. The actual energy is the rate multiplied by the time, power, multiplied by 12.3 minutes. Now I got to convert minutes to seconds. It comes out to be 72 kilojoules.